Right. Okay. So what I wanted to do originally is to create a course for my kids. Carpathy, right? The guy who used to work at, before that he was at Tesla. He was like the head of, I think it's Andrzej Car Carpati. Yeah, I don't know how to say his name, but this guy, I think he has into his YouTube with Mike, and it's one of the best courses, like better in my opinion than Andrew Ong's on, etc. Nothing against the other guys. It's just I really, really like how he was so hands-on. And he has a GitHub also where you can go through it, and he created this mini NLP thing. And I will do the course. It's called Nano. Recommended. He has these YouTube series, etc. I lost my kids' attention because lost the attention of whoever's watching this. Poor souls. But I lost their attention, and so I thought, I want to make it more playful, and I want to make it something that people can actually, the discovery process to be more around tinkering and exploring, and less about listening to a course with a clear objective in mind, right? So like more in the open world of learning AI, right? That kind of stuff. And honestly, it is far from like the final product, right? This is just kind of getting there. And actually, it doesn't even start there. It starts here. And it probably doesn't even start like this. It starts actually more like this, right? So I don't know if this is going to work, the zooming in here. But essentially, they like to start to play a game where they're given avatar, and then how many hours, it's kind of like walking through a story of trying to make things about the world, right? And so the first one was avatar is studying, and based on the number of hours that they've studied, they will get a score, right, on the exam. But the idea is that people are able to like input, they get a test score. And what I want is that there be a discovery journey as to, it's like do it on your own, right? So if I ask you, and unfortunately you're behind the camera, so I'm not like interviewing you per se in this case, but like I would say, and this is really the format that I wanted to take, but like if you study, so like pretend like you're listening to me, right? So if you study 4 hours, right, what do you think is going to be your test score? And I'll just go to this tab just very quickly, but to make it a lot less maybe boring than what I'm doing now, but the idea behind machine learning, right, is that you have something, like you have like a training set. So this is what I've shown here on the screen. So you have like a training set here with 80 data points, and then you have a test set. And at that point, right, you have essentially a variable. So your model, for example, would be X, and it's, let's say, study hours. And then you have, and that's called a dependent variable. And then you have that's called the independent variable, X. And then you have an variable, which would be the score. So it's as if Alice, right, studied for 3 hours, and she got 96%. Bob studied for 3 hours, got 94%, right? Charlie studied for 5 hours and got 100%, and so on and so forth. So you can go through all the letters of the alphabet with all of the students, and then you say, so if I give you a number of hours, right, can you predict for me the score, what the score will be? And then you'll say, well, it's not perfect, right? That's real world. The real world is never perfect. It's not like there's a perfect correlation, right? It's not like it's guaranteed. Maybe Bob was sick. Maybe Bob didn't sleep well the night before, right? So there's a lot of factors. But the idea here is to make it more playful, right? I want people to play, to be able to say, and I'm not going to zoom in here, but to be able to, I will try to predict manually, right? You give me a number of hours and I give you a test score. Or it could be other things. It could be, how heavy person lift, and then how fast they run, and then you tell me how many points they scored at basketball, whatever, like all of those things, right? It's like you make a prediction on. It could be, let's say, whether it rained in the past week, and whether your plants need to be whether your plants need to be watered, etc. Right? Anything really. But the idea here is to show how you can build a neural net. And I'm building here the simplest possible neural net in the world, and I'm going to walk you through it. Okay, it's really cool, and I mean it. When I say the simplest neural net, it's because I think any simpler than that, and it's not a neural net anymore. So Imagine you have 3 hours of study, okay? And then you multiply it by something called a weight. When we talk about neural nets, we talk about ChatGPT and we say like it has like 1 trillion parameter. Well, that's what we mean. We mean how many parameters like this. So it's like 3 hours of study times a weight. And the weight in this case is 1%. What do I mean by that? I mean that every hour of study gives you 1% more on your test score. Okay? Is that a good neural model? Probably not, right? Does it make sense? 1% per hour of study? No, it's probably more like every hour of study gives you 20% more, like most people don't study like 1 million hours for a test. Say 5 hours, 10 hours. If it's a really hard test, maybe more, but like usually like you study the day before, 5 hours, and then you get your score. I mean, of course you study during the semester, but we're keeping it simple here. And then there's a bias. And you're like, what is this bias about? And well, the bias is, that's what neural nets are. Neural nets have this notion of having like a variable times a weight plus a bias. So it's sort of like the most basic equations in the world, right? The most basics are like mx plus b, right? The slope times x plus b. That's what we learn in, and here I'll actually show you like, what do I mean by mx plus b, right? This is on this screen here. Faye, you can go pay attention. This is actually an activation function, but it doesn't matter. This is a slope, right? This is like, there's a slope and then there's an intersect. So my kids don't even have that much familiarity because I don't think that it's cool yet they're doing this, but trust me, in the homeschooling, we do all of this because it's so cool. So then you end up with a sum. What is 5 times 1% plus 1%? 6%. Oh, so you end up with a sum. Wow, neural nets are just math? Yeah, they're just math. And then you have something called an activation function. So if you want, you can think of the sum as the input to the neuron and the activation as the output of the neuron. Okay, so inside of it is a formula. And in this case, the activation is just linear. So that means I input a certain number and you output the same number. Weird, right? That's it. It's just linear. Like you cannot make a simpler neural net than that. So your activation is linear, meaning whatever comes in comes out. F of x equals x. And then you end up with a test score. Well, you studied 5 hours and your model predicted that you were going to get 6%. Is 6% correct? No, you got 100%. So what is the error? The error is 94%. That's how wrong you were in your prediction. Okay? And then you have this measure, which I would love to gloss over, but I'll still mention a few things because it's actually pretty important. Errors, as you can see, can be positive or negative. That's not good. Like if you want to do math on this. So the idea is that you want to have essentially a function that takes the error and makes it such that high error is bad, low error is good, right? So you want to make it positive. And what's one way that you can make it positive? Make it square, right? So the square of the error. So that is what the loss is, if you want. It's the square of the error, right? But it also is interesting because the square of the error not only makes it positive, because now you could say, why don't you just take the absolute value of the error? Well, it's because I want to train my math, right? The math agent is just math. I want to train it such that if you are very wrong, the square of very wrong is very big, right? Whereas the square of not so wrong is very small. So that's why square is also nice, right? So it makes it positive, but it also punishes very negative values, and it doesn't punish small values just as much. Now you might say, why not raise it to the power of 4 or to the power of 100, right? Because that penalizes it too much, right? It's like square is good enough, it's easy to compute, etc. But you could try other things. Like no one said machine learning must use square, but most people use square. It's convenient. And then you might say, well, why don't you use power of 3? Well, because power of 3 keeps the sign, right? Power of 5 keeps the sign because it's odd. Make sense? So then what you do after that, and this is where like algorithm comes in. When we say backprop, when we say like AI is just backprop, this is it. There's nothing else to it, guys. There's absolutely nothing else to it. All it does is it then takes the error, right, or the loss, and it says, how much do I need to change my weights and my bias such that I will decrease my loss? Right? That's it. That's just the question. It's like, I made an error. I predicted 94%, and I know that I'm wrong, but how much change do I need to make? And so you just compute the change, right? So it's a change, meaning, if you remember, Maybe you took calculus, maybe you didn't take calculus, but the idea of calculus is the study of change in one variable as a function of another, right? So in this case, what are we trying to do? We're trying to see the change in the loss as a function of a change in the weight, the weight parameter, or a change in the loss as a function of a change in the bias, right? We don't want to see a change in the loss as a function of the x, the independent variable, because that's actually not what we're learning, right? We're learning the parameters of the neural net, yeah? So now you might say, okay, so should we like instantly correct it? And an easy correction would be that 5 hours of study equals 100%. So therefore, what should be the bias? Well, the bias could be 0, and the weight could be 20%, right? That would be perfect. Well, that would be called overlearning, right? And the problem with overlearning is that if you present a new data point after you've overlearned, you'll probably be wrong, right? So what you want is you want to sort of like learn, but one little step at a time, not like learning it, bam, like I know everything there is to know, bam, and then you'll always be wrong, or you'll be chasing your tail, right? So you want to have this idea of a learning rate, okay? So the next formula here shows how, based on your loss, you want to update your weight. So you start from your current weight, which is 1%, and then you add a learning rate. And now it's just a coincidence that the learning rate is 1%, but the learning rate basically wants to be something small, probably 1% or less, right? That means that you will make, in my case, I have 100 data points. I actually have 100 data points, but 80 of testing, 80 of training and 20 of testing. So I'm thinking, okay, I want to make my way there gradually. If I had like millions of points, billions of points, trillions of points, if I download the whole internet, maybe my learning rate, there's a lot more to say about the learning rate. For now, it's pretty simple. So we'll just say it's a fixed learning rate that every time you update your weight, you update them, but you update them by 1%. So it's like you're moving, it's like you're saying the right answer is over there, but just move 1% of the way, okay? Never move all the way. And if you're making the same mistakes, on 80 data points, you'll kind of move 100% on average about the right way, You don't want to move too fast because you could, like I said before, but you could also, you don't want to move too slow because you still kind of get stuck into like a local minima. It's like you'll never get out of your little hole that you're in. So there's a lot of, like, we're not ready for like the whole reveal of the, everything you can do around this. But here this is very scary, and it just says delta. That just means change. It's like from Greek, it just means change. Like a delta, like a change, like a slope. You put something, the ball rolls down, it changes over time. That's it. It's just saying the change in the loss as a function of the change in activation. It says the change in activation as a function of the weight. And this, ladies and gentlemen, this is what I claim very few people understand. It's like in that I would love to go sit on the street and do an interview and tell people, can you please explain to me the chain rule and the backprop algorithm? I tell you, okay? Most people will not be able to explain it. But it's so simple. It is so crazy simple. All that it is saying is that we're trying to minimize the loss, right? But there's no direct link between the loss and your weight, especially not in a neural net that has multiple layers, right? Right now, our neural net has how many layers? 1, right? It just does the sum, 1 activation. If you had a neural net with more layers, imagine this little thing here, well, the output of the activation could become the input to the next layer, right? And then you can add many layers. And most neural nets are structured such that they're like, single layers, and then the first layer is connected to the next. The outputs of one is connected to the inputs of the next. But you can also do things where maybe the first layer skips the second and goes to the third, right? Like you could have neurons that are arbitrarily connected together. But it's simpler for now to just think about neural nets as being single layer. Just to start, just single layer, single neuron. And so we're saying the change in activation, the change in the loss is a function of the change in the weights. But they're not directly related, right? There's no arrow that goes from weight to loss. There's stuff in between. And what that stuff in between is, that's where the chain rule comes in, right? What we're saying is that you want to understand the change in the loss as a function of the change in the weight, right? And the change in the loss is a function of the change in the bias. But you need, this is the chain rule, you want to have essentially an intermediate thing. And it's just like a fraction. You know when you say a fraction, when you say divided by 2 times, let's say, 4 divided by 5, right? 1 divided by 2 times 4 divided by 5, right? You can take this and you could cancel the 2 and the 4, right? And it becomes 1 times 2 over 5, right? And then you end up with 2 over 5. That's your result. Same idea here. So you just have a middle point, right? And in this case, you have just one neuron, so it's just one activation. So you're just breaking it down such that these things are easy to compute, right? It's just about computation at the end of the day. The chain rule is just a way to be able to all of the little changes along the way, because from the loss all the way to all of the parameters in your neural net, right? And I spent so much time here, but it's so easy to understand when you see simple numbers like this. If I show you a more advanced neural net, and not super advanced, but if I show you this one, and I show you those functions, right, you're going to jump and say, what the? You know, you go, what? Right? So complicated. This is 3 input, 2 layers, and it uses something called rectified linear units. This one is 3 inputs, 1 layer, and it's a little bit complicated. And this one is 1 input, 1 layer. And 1 input, 1 layer, it's so easy to see. Intuitively, you can grab it, right? What it's saying is that what was the change in my loss as a function of my change in my activation? More percent. It's the, like, that's it. Like how much, you know, my loss changed. I think we'll get there. But essentially what I want to show is that we started with a weight of 1%. We made a huge mistake of 94% by stepping in through 500% essentially, and we updated by 1%. So that means that I think 94 times 5 is like 57 or something. Yeah, something like that. And then times 1% is 5.7%. So sorry, it's 4.7%. So we go from 1% as our weight to 5.7%. And then for the bias, we go from 1% to 1.94%, right? So again, maybe I've lost a little bit of people here, and I'm really sorry, but the idea here is that we went from a certain set of weight and biases that were wrong to a set of biases that are less wrong, right? A lot less wrong. So now we can test it again, right? This was our first iteration of testing. Of training, sorry. Now we train again. Now we have another data point. Study hours, 4 hours. We have a new weight, 5.7% and 1.94. We do the sum. So now the engine, right, has a sum of 24.74. We do our activation. Our activation is simple. It's linear. We end up with 24.74. What is our new math test score? Again, 100%. We're wrong again by 75%. Our loss is 28%. It's less than it was before, right? Our error has decreased. And then we do the same algorithm. Our new weights, right? So on and so forth. Learning rate, activation, 7%, activation 100%. So we update it, right? 1% equals 8.71%. And I can't see the new bias because of this thing on my screen. Let me try to, I don't know, something. But yeah, there's a new bias. Actually, I can show the new bias because this is just a view of this. So the bias went from 1.94% to 69%, right? That's all it does. Keeps going. So it feeds data points, right? The 5 hours, 4 hours, and then it takes this 8.71% new weight bias, and it feeds it back to the neural net. So it's here. Right? So that's column F now, is a new data point where the person studied, Charlie studied 3 hours, got 94%. Our neural net, single neuron, linear activation, was 8.79% bias, and it made a prediction of 28%. Was it right or wrong? It was wrong again, minus 65% wrong. And so it updated its weight. Now its weights are at 10.67% and 3.34%. And then we keep going. Now we feed it again. Now we have a new data point. Oh my God, this is Dougie Dog. And Dougie Dog, well, he only studied 2 hours, and maybe something else happened in his life. Maybe his dog, you know, passed away, something. Maybe he's sick, something happened, but he only got 33%. Now our engine, right, says 2 hours times 10%, right, plus 3%, that's 24%. So actually our engine's not that bad anymore. Holy crap. we were only wrong by 8%, right? And so in the end, you'll see our update here is not that, we're still undershooting, but we're now at 10.83%. You see, only 4 data points, and we're already saying that every hour of study should add 10%, right? Plus a bias of 3%. Next data point, so I want to protect my voice, so I'll skip ahead a little bit. And we'll go to like, the next one was 9%, 10%, 12%, 14%. And then you see it's kind of stuck at 14%, then it goes to 14%, 0.64, and the bias kind of stays stuck a little bit. See, there's 80 of those points. So you'll see it actually goes up and down. See, it even goes down here, but you see eventually it kind of oscillates. And it ends up being in a happy place of 15% per hour studied and 14% of bias. And now we have a test set, right? Because we train on 80 data points, and now we have a test. We have 20 points of testing, okay? So you start with testing, you're not changing the weights anymore. So you see, so we don't have the backprop here, right? We had the backprop and the chain rule and then the weights. We no longer have this. Now we're in production, right? Since we're in production, we only measure the error and the loss. But the first one studied 0 hours. Said when you study 0 hours, you're going to get 14. But he actually got 52%. Hey, this guy, you know. He didn't study, but he got a good grade. He's good at guessing. I don't know why I say it's a guy. Could be a girl too. But we got it wrong. But overall, if you look, we got it pretty good, right? Like, it's not bad. It's decent. Like 34%, 73. Okay, that was wrong. That was pretty wrong. That was pretty wrong. But it's not like as bad as when we started, right? 57 got 43, 99 got 87. So we see that our engine, you know, it only has one parameter. So now you might say, well, if we knew more about people, we could do better predictions, right? Yes, you could. So that's what we're going to do next. We're going to improve by same data set. In fact, this data set, I didn't tell you this, but it was not generated here. It was actually generated in the next model. Okay, I'll skip over this here, but actually I won't skip it. This is a measure of, if you want to know across all of the test cases, how much loss did you have? Well, you'd have to like add the loss and then divide it by the number of data points, right? It's sort of like if you want to know how tall is the average kid in my class, well, you'd say, well, how about we measure all of them, and then we'll add up all of their length, and then we'll divide it by the number of students, right? That's the average. So that's the same idea here. That's the mean, right? In this case, however, we're doing something slightly different, where we're saying we are adding up, right, losses, because remember the losses are not the errors are not all the same signs. So we're adding losses, but losses, wait a second, were squared. So does it make sense to add square? No. So you want to take the root. What is the root? Well, the root is, you know, the square of 2 is 4, while the root of 4 is 2. The square of 3 is 9, so the root of 9 is 3, right? So you want to take the root of the square. So you're going back, but you lost the sign, right? So it's an effective way to sort of say, I want the root of the mean of the square of the error, right? Root mean square error. That's all it does. It's just a measure of how wrong were you on average, right? So we were wrong on average at 22%. Is it exact that you should expect that your error be 22% off? No. It's not exact, but it's good enough. Like, there's no perfect measure of evaluating the quality of a model, right? Like, it's just like there's no perfect way to say how good is ChatGPT's model, right? There's no perfect way. So what they do, in the case of ChatGPT, for example, is they did go and try to, let's say, pass a medical exam test, right? Let's see how well it does. And, well, it scores better than any human alive, right? It absolutely massively demolishes the test. Meaning that ChatGPT 4.5 is probably better than any human alive, definitely, I think, at passing any medical exam you want, any actuarial exam you want, etc., right? It will get all the answers right. Now you might say, well, does that mean it's smarter than us? No, it just means that it learned it from the data, right? It's just in the data if everything is there. And it's because the tests are actually more like knowledge, and there's not that much reasoning into it, right? If you want to see these tests fail, they have to do something that humans are really good at, right? And what we are really good at is more things like really advanced math, right? So really advanced math, they fail, right? So the best, most difficult computer, programming tests there is, things like code forces, they will fail, and they will continue to fail forever. Why? Well, forever is a strong word. I'm not sure if it's forever, but certainly with backpropagation, because backpropagation only learns, right? Its inference is only learning based on what it knows from the example it has received. Now you might say, yeah, but it can generalize to other concepts. Yeah, but it does not generalize as well as we do, right? It's not the same. It's more like its generalization is within the dimensions that it has been shown, right? So it can sort of like fill in the, as long as it saw one dimension here, one dimension there, it can generalize here. Not very strong, but well enough. Whereas humans, it's like we're able to like create whole new dimensions, right? We're just like higher dimension. Our brains, I think, are, I'm not sure if we're able to represent all dimensions of the universe, probably not, but we are way more high dimension and creative than it can be, right? Way, way, way more limited is my strong hypothesis here. And so we won't see that for time. I would love to see it, but I don't think, anyways, that doesn't matter. But I would bet a lot of money, and I'm betting a lot of money with bld.ai that, well, yeah, they're just not efficient enough. Like you can add, GPUs become too expensive. Even if I had a huge context window, if I could put 1 million GPUs together, right, it would be extremely expensive, but like 1 million GPUs working together for one inference case, for one query, right? First of all, you'd have to train the neural net, and it's, it would be almost like a big neural net, but all the resources in the world, in one neural net, all the resources in the world to make inference on that neural net. Inference is like testing, if you want, whereas training is training. So if you had all, and usually like it takes less, you see, like, this is like such a nice, simple thing, but like, well, right there, you see it on my Google Sheet? It's less expensive. It's pure formulas, right? Because you're not like computing the backprop, you're not doing the chain rule, you're not updating the parameters. Yeah, so it's like, is it half? Well, on my sheet here, it's about half, but like different. No, it's definitely not, right? Well, it is about half, to be honest, kind of. But what you have to understand is that when they train, they don't train on 80 data points, right? They train on like the whole. So they feed to it like a lot of data, like little text. There's a lot of iterations. So it's, let's say that it's, I don't know, 1 billion iterations, right? I don't even know. I have no idea. I should know those numbers better on how long it's trained. But when you test it, it's just one single one, right? So that's why the testing or the inference is a lot less expensive. The inference per epoch, right? Per when you run the network, it's less because it just like feed forward. It doesn't like feed back, right? It doesn't do the backprop. It just does feed forward. But also, it's you're just doing it once or twice. Actually, when you use a GPT, it's not just one, right? When you use a GPT, it predicts like one token, and then it feeds the whole thing back, and it predicts the next token. It feeds the whole thing back, predicts the next token. So if you have like a long context window, it actually runs the network many times until like, sorry, not the context window. The context window is like the input. If you have a big input that's bigger, it will feed a part of the input, and then feed the next part of the input. Like it like feed the network many times on the input iteratively, and then you can expand that with a RAG, right, retrieval augmented generation, where it will have like a little part of its input will be indexes, like Google searches on like a bigger data, bring some of that context back. But the output itself, like you feed it many times and then you increase the output window. Anyways, completely out of context here, just a big parenthesis. But yeah, so for our test here, we use root error, and on average it's, let's say, 26%. Now if you go to the next part here, what I did is that I said, okay, what if instead of just study hours, we also have sleep hours, and we also have is sick? This is where I actually generated. This is the real underlying model, if you want, the hidden model, right? It's as if I have the keys to the universe and I am God, and I have defined a model that basically is super simple, right? It's just saying, if you're sick, I give you a score between 30 and 60. If you're not sick, you'll get at most a score of 100. That's why I do minimum between 100 or something else. So at most it's 100. And it says if F3 is greater than 3. So if you've studied more than 3 hours, you'll get 70 plus 5 points for every F3 plus 2 points for every F4. So 5 points for every study and 2 points for every sleep hours, plus a random number of plus or minus 5%. right? So that's the real magic behind it. Like, I could change that, and I could change it on the fly, recompute everything, all my neural nets would be computed. But all that I wanted to do is to create a somewhat complex nonlinear model. You see, because life is not linear. It's not, you know, this is a nonlinear, this is more of a representative, you know, aspect of life. It's sort of like, there's a minimum, like, what it's trying to do is like, it's sort of trying to say, I have 3 variables that I'm trying to represent with some model, right, some digital twin of reality, of like, what is it that if you know, if you study less than 3 hours, there's sort of something about life that it's like, you'll probably get 0, right? But if you study like or not 0, but like, probably you won't be able to get more than 60, essentially. What I'm saying is that if you're sick, it's going to be very hard to get more than 60, less than 30, because, you know, you can kind of guess your way, right? It's multiple choice or whatever. But if you're not, you know, it's very discrete, right? It's like if you're either sick or you're not sick, right? And that's hard to capture with just the linear model that we had, which was just number of hours studied, right? So now we have like another variable, which is sick or not sick. But it's very discrete, right? It's sick and not sick. Now, number of hours of study is more like continuous, right? It's smooth. But even that, in reality, is not exactly smooth. Like, you know, learning is not like 1 hour, I get 1% learned. 2 hours, I get 2% learned. It's more like I get 0, you know, I don't understand anything, until suddenly it's like, boom, and then you're like, oh, I got it. And then you probably overestimate how much you got. You're confident about your mastery of quantum physics. And then you start to be like, oh no, I don't understand anything, right? Like, you start to doubt yourself. But there's like this suddenly that like you got the standard model, right? Like, you get gluons, you get that fundamental, you know, the random nature of the universe, etc. Observability, Heisenberg uncertainty principle, etc. Like, you get like this big sort of explosion, but then it's not just that, right? There's still some other randomness which we're not carrying here. So that's a little bit the idea here that I was trying to model very, very simply. Right? And actually, I asked ChatGPT, I kind of described it, and I said, can you give me like a random formula that would be super simple and easy to explain, that can, you know, that can help and would allow me to demonstrate that a single variable network, there's a multi-variable, also that I need a discontinuous nonlinear function. It'll bring us the So, you see, it started also at 1%, but this one was 1% for weight 1, 2, 3, and a bias of 1%. I could start it at whatever, right? I could start at minus 100. I could start at 1 billion. Sure. But it doesn't. It's really robust. I just like to start at 1% because it's like nice for storytelling. Yeah. So you'll see it went from 1% to 4.9% for the first parameter, 5 for the second, and 1 for the last. And you'll see that's interesting because sick, as we know, should like take you down, right? But here it's actually not updating it at all because it doesn't have any data on it, right? It's like the sick weight stays at 1% until the sick weight shows up, and then it decreases it to 1%. And how much is it going to decrease it? I'm sort of jumping ahead here. But eventually, oh, see, it doesn't really pick it up. It kind of goes into the negative space, which is cool. It realizes that it's negative, but it doesn't do much about it, right? Oh, a little bit more, a little bit more, a little bit more, a little bit more, and it never really learns the sick one, right? So it thinks that when you're sick, it's just minus 2%. And it thinks that like your study is 9% and your sleep is 3%. Again, it's a linear activation function, so it's just a sum, right? It just multiplies whatever is the end parameter. So let's say 5 times 3 times 9% plus 5 times, actually this is funny, times 3%, and then 0 times minus 2% plus the bias, right? Now let's see how it did on the testing. Right, so first case study, it said that is very wrong. It said that the guy studied 3 hours and slept 6 hours, was not sick. Model predicted 27%. That's really not good. He got 97, that bastard. So very wrong. But that's okay, right? We do the best that you can. And then now the question is this better than the single variable one? I don't know. Let's go. You're in the way. You're in the way. You're in the way. You're in the way. How do I? Oh, I could like bastardize my model for a second just to show. There you go. Yeah. Okay. So 25% root mean square error, versus here, 32%. So it did improve. Does that mean it will improve every time? No, not every time. Right? And you'll see the number change because I have some randomness. Like every time I delete stuff, it like recomputes, right? So if I were to like insert something, you see oh no, it does not recompute. Oh yeah, it does recompute. Yeah, so this one's at like 27%. This one is at 45%. So this case, it's worse, right? It's interesting. But I can tell you that it's not clear on the linear model whether more variable is better or worse. It depends, right? It really depends on the activation function. But in general, a good rule is that, and there's something called like ridge regression and lasso, and people that won Nobel Prizes and etc. But there's something about how you can sort of like in a regression, you can pick in like a nonlinear combination of parameters to predict a function. You tend to want to pick the fewest number of parameters possible because they generalize better. And there's a way to like measure which ones to throw out, right? There's something called ridge regression or a lasso. Those are both things. The guy who invented lasso, I think, is like some guy at Stanford who like won Nobel Prize and like has a super high H. I think because he's in the medical field of publishing things. So, but yeah, it's called lasso. Very cool. But I don't think like that people would say like it's crazy, super, like, it's worth knowing. I think I like using ridge. You can learn Python, sklearn. It's all there. But now we go to we bring the miniguns, right? The first one was like so simple. It's like a rock, right? Single variable, single layer. Then the second one was like a stick, if you want. 3 variables, linear activation. This one is 3 input variables, 2 layers, where we have 1 layer that is nonlinear. So what do I mean by a layer that is nonlinear? And now I'm going to bring this little guy here. What do I mean? So this is what I was saying when I was saying like activation function. So the activation function means this is like your input, the sum, and this is your output. Okay? So it's saying if you feed me 1, I give you 1. If you feed me 0, I give you 0. If you feed me minus 1.5, I give you minus 1.5. Right? So I spit it out. And now what we wanted to, but it's hard to like make arbitrary predictions if the nature of what you're trying to predict is we want to be able to combine, right, things that are nonlinear. So this is the one that we're using, ReLU, okay? It's so simple as it just says, you give me 0.5, I give me 1.5, I give you 1.5. There's something weird here, I don't know why. But ReLU, you can kind of look at what it looks like. ReLU is this one. So ReLU is the max of 0 or the value, right? See, the linear is the value. Whatever you feed me, I output. ReLU is the max of 0 or what you feed me. Meaning, if you feed me negative, I cut it off, I just give you 0. That's cool, right? So it's very simple. Very like, you can create hard, GPU hardwares, etc., that can implement and compute it really, really fast. And it's nonlinear. And it's nice because it's nonlinear, like you're able to like express yourself more. Like have neurons that are like expressing positiveness in one way, and then neurons that express positiveness in the other way, right? It's like a bit more sharp in terms of its expressive power. So let's see how ReLU did. Okay, so I can run us through all the things, but again, I should save my. But I won't show like all the details. In part, probably make a lot of mistakes as I walk through them. I'm tired. My voice is down. But enough to say that it's the same idea. Okay, same idea as what we started here, where you have a bunch of input parameters. Okay, then you have a bunch of weights. There's more weight. There's one that connects H1, which is your study hours, to X1 to H1, right? It's like your first neuron. Then X2 to H1, X3 to H1. Then X1 to H2, right? You can think of this as like the other neuron. X2 to H2, X3 to H2. And then, that's the first layer. Then you have the second layer, which is H1 to output, and then H2 to output, right? So it's like 3 input parameters, 2 middle layers, 1. The one that just has 1 is a where is it? Sorry. I think it's a linear function. Yeah, okay, here it is. So it's a linear function, whereas this is ReLU. This is where ReLU is. So the ReLU is in your H1. So your change in your H1 is ReLU. Change in your H2 is ReLU. But you change in your output linear. So we made it like ReLU, and then output linear. It doesn't matter. Like you could, I mean, it does matter. I could have done like ReLU, right? I could have done 3 ReLU, or I could have done 3 linear. I could do any of those, right? Every neurons are like snowflakes. You can make them whatever you want. You can give them whatever activation function that you want. You can do tanh, sigmoid, ReLU, leaky ReLU, GLU, and I could do a whole video on like 1,000 other activation functions. But what really matters about activation functions, I guess 3 things. One is like how easy, you don't want complicated ones, right? You want as simple as possible. Second is its performance in terms of, you know, Xmas, if you want. And then the third one is like derivative. Like how easy is it to like smooth it out and to, you know, to learn essentially. Because you could have really, really powerful activation functions that would be like impossible to learn. Not very useful, right? So you want them to be like easy, like you want them to sort of be, and this is why you have like weird curves, and I can just kind of show it like this. This one's kind of cool, like you see how GLU like has, it's like a hockey stick kind of thing, and etc. And they kind of have this thing where, like when you do the backprop in the chain room, where you are computing is changing one variable versus a change in the other. So these nice slopes. Everybody likes a nice slope, so that the, you know, you can easily have, you know, as the neural learns, it sort of easily finds its happy place, right? You want it to find its like smoothly, you know, as it's all related to, etc. There's a lot of this has way more interesting. You know, science on like how you do it and what you do when neurons become zero, you know, like dead neurons, because you don't want to stuck. So there's a lot of science there. But not an expert. Should I say I'm not an expert? Because ChatGPT is better than me at this. So the day I can beat ChatGPT at this, I'll call myself an expert on data science. I don't think there's very many experts of data science in the world. I know a few. And they truly are better than ChatGPT. Like you ask them a question, and trust me, their answer is going to be better than ChatGPT on data science concepts and like, you know, what's cutting edge, etc. And then you'll like point it out to ChatGPT, and it'll be like, oh, yeah, I guess you're right. Or sometimes it's just even not going to. It's a little bit like, you know, sometimes when you talk to these engines, because and those are easy to spot, right? But sometimes it's much harder. I think it gives people a lot of misplaced confidence they don't know enough about. Anyways, but when you do have it, when you do know wrong, then it's very frustrating, right? Because you're like, how dare you be wrong? Well, it doesn't know, you know. Do it, you know, it's missing information. Anyways, this is what it does here. It's much more work, but it's the same idea. So we start with a feed-forward pass through our network. We compute activation. Activation started at 1.3, so we had a lot of error, right? 51% error, and you'll see this 51% error here is the same as like, you know, over here, the error is 43%, but it's the same idea. Here it's at, you know, the error is 52. Every time I change, right, it kind of recomputes the model. But then you have the backpropagation where it says, you know, what's my change in loss, and then bring it back to my, bring it back to my weights, and then it updates the weights. And then it does that, and you'll see over time, all the way until the 80 data points are trained. And, wow, look at this, 13.8% root mean square error. This neural net, actually, this is a very legit neural net with 3 neurons, 3 inputs, 2 hidden neurons, 1 output neuron, so 2 layers in total. It performs better. It's built in Google Sheets. All the numbers are there. It performs better. Right? It has slept hours, study hours, is sick, and it's able to do I mean, not a great job, but a pretty good job. Like, I'm pretty sure that if I were to just, like, if you just ask me, right, hey, this student right here studied for 6 hours, slept for 5 hours, and is not sick, what's his score? What's her score? I would not be as good as that thing. No way, right? And I'm not saying like this thing because maybe I'd be able to be like, oh, looks like a geeky Chinese student, probably good in math, right? I could also use like all my stereotypes and probably improve it, but that's because I have more information, right? I'm saying if I didn't have more information, if all the information that I had was the data that's here, right? And like that's why I was saying, like, I want my kids to learn this by playing with it. You know, I want to make a game such that they're like, oh my God, I was able to like build with these building blocks this thing that beats me, right? That's the cool part, is that they'll have this discovery, this like, aha, wow, that like, this thing is actually really good, given the information that it has. This neural net is actually really good. Like, and I would like to test people, right? It's sort of like if I say, like, let's say that I hide this thing here, right? That I hide this thing here, like this. And I say, okay, now I don't know what it is. And I will hide this thing here too, right? And then I would go and I would say, here, I'm going to give you a bunch of inputs and go write down your prediction, right? Just using your intuition, just using that big brain of yours. You know, I'll let you go look at all the training data. Now I give you the testing data, right? This student slept for 3 hours, slept for 3 hours and slept for 8 hours. What's their score? And you'll be like, I don't know, 42%, 52%, you know. You will lose. Does that mean that this is smarter than you? It doesn't mean it's smarter than you. It's predicting that because, yeah, it's really clever math, right? It's very good statistics. And so that's what it's all about, right? Like these AI engines, additional ML engines, and this large language model. That's what they're very good at. And that is the end of lecture number 1. I need to go drink some water. Thank you.